go out.
Oh, yeah. No, it was, anyway, I'll just say, first of all, welcome to Lecture 5. And his name is Brad Van Wert. He does solar installation out of Bozeman.
Mm-hmm.
And it was cool. He just kind of bootstrapped himself, said, hey, I'm doing a whistle stop tour, brought awareness to a lot of programs around the state. There's one called PACE. I don't remember exactly what that acronym stands for, but it's basically special loans, specifically for renewables, and he was focused mainly on PV. And one really good takeaway, he came into our Energy Y 243 course, PV installation, looked at the materials like this is exactly what the industry needs. You guys are sitting on a gold mine here, just stick with it. So, yeah, and then I think he's also involved with this group out of Ann Arbor. There's a professor there who either owns or has access to 7 acres of beachfront property in Sri Lanka. And after a civil war there a few years ago, he and some colleagues invested some money to build an orphanage for some girls who were orphaned after a civil war. And they're all approaching employment age, in their late teens, early 20s. And what they'd like to do is start a solar PV installation business with these young women. And I've never been to Sri Lanka, but apparently there's a lot of ecotourism that happens there, and so people show up, and then all of a sudden there's these diesel generators and things running to keep the lights on. Like, that's not really what I signed up for. So they really think the market is ripe in Sri Lanka to have a local industry start to do this solar. So
Very cool.
yeah.
Yeah, I wish I'd have had the chance to be here, because I've been following him on Facebook for a while.
Yeah, he's something else.
Yeah.
And what I really like about him too, he puts a positive spin on everything. It's like this is going to happen. It's inevitable, and just got to keep moving it forward and be positive. So, no, I'm pretty lucky to have someone like that around. Yeah. He himself, it was kind of an interesting story. He himself was a roofer, so he didn't have any formal training in PV. But he's up there on a roof. He's like, I touched the panel, and I was a convict. I never looked back. Whatever. Yeah, so he doesn't have his NABCEP certification, so a lot of it's self-taught, self-educated. But he definitely said for when he hires people, he looks for that certification. So stay in school. All right. Well, let me.
My summary will be complete before the day is through.
Nice. Yeah, and also just a shout out. I think the due date for the summary was had to be reset, so that's all set now. You can submit at will, and I'll grade it. I'll grade your summary 1 later this week or before class next week. So, and I noticed there were not too many discussion board items, so post it there. Get some discussion, and yeah.
Sounds great.
Good. Thanks. Okay. Well, what I thought we'd do, since we've covered chapter 1, so you're all set on that for the exam. We've covered Solomon, so you're in good shape on that. I think I'm just going to launch into chapter 2 because we only have today to cover it. So again, I'll just hit the highlights, and then I'll hit the highlights of chapter 3 on Thursday. Kind of let you know what's most relevant
Did you finally
for
get
the
the
exam.
recorder to work?
I got the recorder working. Check it out. It's working right now. We're live at 4 minutes and counting. Yeah. I got the camera working too.
Did it not work on Thursday?
No, so this is typical. So the university subscribed to a new version of Camtasia, and whatever, it was still buggy.
Right.
It's working though. So, but on that note though, since you asked about Thursday, one problem that we did that was sort of unique is I had everybody sit down and this is nobody heard this except a few people in the class on Thursday, but the problem I threw out there was to calculate the number of square meters that it would take you to survive if you're going to use 200 megajoules per day. I think I have a copy of that.
We got like how many?
We got 11 square meters, and you nailed it too.
Yeah.
Yeah, and you nailed it too.
Very good.
Yeah.
I took a way different route too when you actually showed us how you did it.
Yeah, well, there's
Yeah.
different paths to solution.
Yeah.
I think I can pull that up. I remember doing it on a.
And there's 1,000 watts per square meter.
Yeah, I remember doing it on an Excel spreadsheet. Maybe I still have that.
So, am I correct when you have a degree in biomechanics? Is that correct?
Are you asking what my degree is in? I have a degree in mechanical engineering with a minor in writing, and I've got a master's in mechanical engineering and a PhD in biomedical engineering.
Biomedical.
Mm-hmm.
Does that have to do with physioactive structures of human beings, or
I took a lot of genetics. I took a lot of molecular biology. So yeah, yeah, took a lot of physics.
Be interesting to touch base on that with you.
Yeah, I had a really good conversation about that last night with someone who was trying to figure out sort of the connection between pain and lactose consumption, which I wouldn't dug into. This might have been it. I've been having some issues. Nah. Anyway, the number we came up with though is if you, and I'll just type it out really quickly so everybody gets that. So what we were looking at was 200 megajoules per day. And we had 1,000 watts per square meter. And we had, did I say 5 hours per day?
Mm-hmm. Yeah.
5 hours per day. And what that came out to be was that the solution was that you would need 11 square meters. So the equations we basically used, we started with area equals the power divided by the specific area. So this is P sub A. Hey Daniel.
Sure.
P sub A equals that. So here's one equation. Yeah, here we go. It's actually pretty simple. There's one equation. The other equation was E equals P over T. Or, I think what we actually did, we said P equals ET. Then we ended up with A equals ET over PA. Is that right? That's right. Yeah, that's right. So the question was, you need 200 megajoules per day, and you're going to get it all from sunlight. The specific power of the sun per square meter is 1,000 watts per square meter, and we're just going to say you've got an average of 5 full hours of sunlight per day, as a rough estimate. And that's a pretty good estimate for a lot of Montana. Then we said that area equals the power divided by the power per unit area. We said that energy is power divided by time, or power equals energy times time. So we do not know power, but we do know everything else. This is what we're looking for. We're looking for the area. So this is one equation. And So pop quiz. Pop quiz. Is what I have highlighted one equation or two equations? It kind of looks like two equations, but it's the same equation written two different ways. Because the same three variables are there, E, P, and T. So there are three chunks of information, and if you know two of them, you're going to find out the third. And it doesn't matter, the only key here is that typically what you do when solving an algebra equation, you put what you don't know on the left side. The rule, everything you do know goes on the right, everything you don't know goes on the left.
That equation on the left could also be graphed, could it not?
All of them can be graphed. They're just simple linear equations, absolutely. Yep. Yeah. So both of these are the same equation. So this is equation 1. And you could say either this is equation 2 or these are equation 2. It's a matter of semantics. And then from there, we didn't know power, and we don't necessarily need to know power. So we just got rid of it by substituting equation 2 into equation 1. And then you plug in your energy, which is this. E. You plug in your P sub A, and you plug in your T. All right? So you know E, you know P sub A, and you know T. They're all sitting right here on the right-hand side of the equation, and boom, out comes the area. So when you run those numbers, we got 11 meters squared. Another thing that's key to thinking about that is basically that 11 square meters, however you want to think about it, that 11 square meters is your, it's not your carbon footprint, it's your photosynthetic ceiling. It's like, I'm going to need this 11 square meters, guys, sorry, because I need to charge my cell phone, charge my laptop, manufacture some gasoline out of the hydrogen and carbon that's in the atmosphere right now, somehow, it's there, but I need energy to recombine the molecules, and that's how many, like photons, how big a patch of photons I need. Okay, so that's the kind of the big picture on that. So now I will save that. And if you want to do a little more research on this, and I know I've mentioned this individual before, but if you go out, and I've had a good time emailing back and forth with it, I'm just going to call this the photo. It's actually pretty small. 11 square meters is not very much. The issue, what's the hidden issue here? Well, efficiency, right? Because if I actually need that much energy, and I'm going to get it all from, say, solar panels, I'm going to need 5 times that much area if they're only 20% efficient.
Yeah, because with this problem, you're saying assume that it's 100%.
Yeah, exactly. Assume that all that nice sunlight comes in and does my work for me. So that's the lower limit of the photosynthetic ceiling, as you might call it.
So the time would be the increasing or decreasing variable?
That is a very good question, because time, we're assuming that you're getting this on a daily basis. And if you remember, the very first problem we did in NRGY 101 was to say, well, where are those carbon bonds coming from? Well, they're coming from underground. When were they put there? A long time ago. So you're sort of borrowing from ancient time, if you will, ancient energy stores. So that's a good question.
So we're definitely capable of skipping those steps.
We're capable, yeah, we
Of
certainly are.
mining it, of
Yeah.
transporting it.
Yeah. Okay, so, and the individual who coined the phrase photosynthetic ceiling is Jared Diamond. And anyway, he's one of my go-to guys. Okay, so with that, I think we're caught up on kind of the key stuff that I did not capture on camera last week. So let's get into chapter 2.
Can I ask you a quick question about that term?
Yeah.
Photosynthetic ceiling?
Sure.
So that doesn't mean a ceiling is in like a cap or like a stopping point. That means just like a surface area that
Good question. So the question is, what does the photosynthetic ceiling actually refer to a physical structure, like over your head? The answer is no. I mean, I know I oversimplified it, but that's one way. It just means that you cannot. Well, here I'll just demonstrate it like this. So we're standing down here on Earth, and we're kind of, you might call the surface of the Earth like the floor, because I mean you could dig into the basement or go a little lower. But let's say I wanted more energy. You ever tried the trick where you're trying to fill your water glass faster at the tap, so you push it up to the tap? But you're like kind of playing with how fast the glass fills by pushing the water glass closer to the tap. And so you could do the same thing, like, gosh, I want to get sunlight faster. I'll start running up towards the sun to get closer to the ceiling.
You're saying like putting solar panels higher up in the air. Is that
No, I'm actually saying by moving towards the sun faster. You might say, oh, I'm going to get sunlight faster if I move towards it.
Okay.
But you can't. You're kind of already there. I mean, we're kind of already exactly in the right place. We're yeah. So the photosynthetic ceiling, you might think actually is more of an area of how big that surface area has to be.
Okay,
Yeah. So I guess the photosynthetic ceiling itself does not have a dimension. It's more of a concept to say that you can't break through it or go beyond it or whatever. So
Okay,
yeah.
Okay.
Okay.
Excuse me.
Yeah.
Are we missing a variable? Because the last time we did it, didn't we have some, so you have 200 megajoules in a day.
Yeah.
You have to divide those 200 megajoules into hours.
You could.
Or, I mean, because that'd be 40 megajoules, and then you divide the 40 megajoules by 1,000, that's how many watt or square meters you would need?
Yeah. Let's do it this way. I'll show you another fun little way to do this. Let me insert a table. Let's insert a table. So here's one way to do it. So we have 2 times 10 to the 6th joules per day. Yeah, this is kind of how I like to write out my equations. So I've got 2 times 10 to the 6 joules per day. That's 2 megajoules per day. And then I've got, let's see, so I've got 1 day here. I don't want to have a day sticking around. And I've got 24 hours per day. That's another way to do it. And then I've got, actually, it's probably easier to do this. Let's just do.
Does it didn't specify whether we wanted seconds or
Yeah.
minutes or hours?
So I got 5 hours.
Well, we were meant to, since all you have is the 1,000 watts per square meter, that's all you have. You just have 1 square meter.
No, I have 1,000. Well, I have 1,000 watts for every square meter.
Yeah.
So if you want to consolidate 2 million watts,
2 million joules.
joules,
Yeah.
in 5 hours, you have to choose this many meters to produce that. You
Mhm.
said it was
Mhm.
11 square meters?
Yeah, I think that's what it comes out to.
Kind of converting the megajoules per day to the watts, so then you know how many watts per day it is that you're using, and then you can
Yeah. So if I got 1,000 watts and I've got per meter squared, I realize we actually did get through chapter 2, so I don't mind taking a little more time on this. One day. Actually, let's get rid of this guy because I don't even need that. Delete columns. So there's joules per day, hours per day, and now somehow I've got to get joules per second. Let's see how I can do that. So if I can do Yeah, so I can do 1 joule equals 1 watt second. It was a lot easier on the board. Now, okay, so now the thing is, so the days.
And then you put in the 3,600 seconds an hour.
Yeah, I think I'm just going to get rid of this for days. And then joules. So I kind of need to get rid of seconds, don't I? Okay, so I've got 24 times 3,600. Seconds. And here's 1 day. I think that does it. So let's just try it on the calculator. So 2,000,000, that's 2 million, times 5. Oh, actually, is time, well, you know what, maybe, I think time needs to be on in the denominator, doesn't it? Kind of did that in a little bit of a hurry. A equals, well, let's just try it, see what happens. Times 5, divided by 1,000, divided by 24, divided by, 3,600 equals times 25. What did we do wrong? It was so easy last time. Can I see your notes?
Yeah, sure.
It was so easy
Yeah,
last
especially the
time.
way I did it was way different too, so I just started with joules, right? And I
Yeah.
know that a joule is a watt second,
Mhm.
so I know I've got that many watt seconds, right? So then, what I did, so then what I did is I took the watt hours, right? So like I divided the watt seconds by
Oh, okay.
seconds, so
You
then
got-
I got watt hours.
You got 1 hours.
Divided by 5 hours gives me watts, and then divide that by how many watts per meter, that's how many meters.
How many
So like,
joules?
yeah, I just did a lot
Gotcha.
simpler, I didn't use any of those.
Gotcha. Okay, let me just take one little pause here. Thanks. Okay, we found the error.
Okay.
I just transposed one of the equations. So,
It's 200.
I got 1,111,112, when you divide all that by 1,000,
Yeah.
and then somehow
You get 11 if you divide it.
it's by 1,000 again.
So it's like 11,000 divided by 1,000 this one.
111.
yeah, so that one conversion there, it was not written explicitly, but you do have to convert hours to, you have to convert hours to seconds. So, again, we've got, super. It is good to review this because there are a lot of different ways to make a mistake, and I just was guilty of one of them. But so that's your energy per day, 200 megajoules per day. Each day, you have 5 hours of sunlight. So the way to think about this, if you had more time, you would need less area. So a bigger number on the bottom gives you more. And then this one's a little confusing, but it's power per square meter. So 100 watts per square meter would have been in the numerator. We pop it up to the denominator. That's where your per square meter comes from. And then to get rid of the hours, we cancel H there, cancel H there, and we're left with, so there's a strike through. Yeah. Y. And then, of course, a joule is a watt second, so that cancels. All right, we definitely earned that one, thank you.
Mhm.
Okay, and then what you end up with is 11 meters squared.
But you divide it by 1,000 more than once. There's 1,000 times 3,600. That's what's throwing me off.
Now, let's do it one more time. Let's just do it one more time on the
Yeah,
calculator.
okay.
Yeah, so
I
two,
imagine, like,
2 million, or sorry, you know what, it's 200 million. I think I was making that,
200 million,
it's
so
200
I
million.
was off by a zero, I put.
Yeah, so there's 200,
Yeah, one extra zero.
there's 1,000, there's, oh, yeah, okay. There's my other little error. It's 10 to the 8th. Yeah, 2 would have been 2 million, but it's 200 million, so it's 2 times 10 to the 8th. Okay, so 2 times 10 to the 8th,
200 million.
200 million.
would be
200 million, divided by 1,000, divided by 3,600,
2 times 10 to the
divided by 5. There we go. Yeah. Yeah, and so, yeah, there was my little errors. I had 10 to the 6th and 10 to the 8th. Okay, that'll do it. Well, let's pause there, and then I realized, I think we did get through most of Chapter 2 last time. If there are no questions on Chapter 2, I'm just going to dive into Chapter 3.